mineral resources and their mapping. She is currently involved in European and national projects focused on critical minerals for the ecological transition. Additionally, she teaches at the University of Granada and actively participates in outreach initiatives and in the Women and Geology Commission of the Geological Society of Spain. She is also a member of CSIC IGME in the IGME's Metallogeny Expert Group. Concha, you can start now your presentation.
Thank you very much. I'm sorry for the delay because technical problems are always appear in the last moment, so I'm not an expert, and this is okay. Good morning, good afternoon. Thank you everyone for joining. As Virginia told us, my name is Concepción Fernández-Leyva, and along with my colleague Paula Adánez are going to explain the START project, particularly focusing on the selection, sampling, and laboratory tests for the extraction of the tetrahedrites in mining waste. This workshop is the result of the work carried out by the team shown on the screen. You can read the names, but we'll introduce later the people involved in this team. By the way, the real name of the project is Sustainable Energy Harvesting System based on Innovative Mine Waste Recycling, START, Sustainable Energy Harvesting System based on Innovative Mine Waste Recycling. Okay. First of all, I want to start by simplifying the general objective of the project, which is, as you can read on the slide, to transform mining waste into an energy resource. On one hand, as you can see on the left side, representing by iceberg, the residual heat is a waste energetic source, and on the other hand, on the right, we have represent sulfides in tailings dump, which have always posed an environmental problem. In other words, the principal aim of the project is to convert tetrahedrites discarded in waste dumps into waste heat recuperators. So that's it will be the main idea of the project. Okay, how will we organize this workshop? First, we will discuss the project itself, the framework in which the program develops, how the idea came up, which is an interesting point to mention, how it is funded, who makes up the consortium and the partial targets, among other aspects, okay? We will also cover some basic concepts, such as residual heat and what a thermoelectric device is, for example. And finally, we will focus on the work carried out within the work package related to sampling and obtaining the concentrate, the work package 2. As you can read, within this work package, some activities have been carried out, focusing on both fieldwork and laboratory work. As you can see, they are organized into different stages, 1, 2, 3, and 4. So in this workshop, we will explain all these stages in detail. Okay, well, in this slide, we have gathered the general information about the START project. As you can read, is under the Horizon Europe program included in Pillar 2, Global Challenges and European Industrial Competitiveness. It is inside Cluster 4, Digital, Industry and Space. Additionally, as you can see, this project involves 15 partners from 10 European Union member states and 1 associated country. The coordinator is the Geological Survey of Portugal, LENEG, and it will be active for 4 years, from 2022 to 2026. And the budget is 9.2 million euros, co-funded funded by the Horizon Europe. Okay, among the partners, there are 5 European geological surveys with a strong background and knowledge on geology, as you can see on the screen: BGR from Germany, LENEG from Portugal, IGME-CSIC from Spain, UU from Austria, and SGUDS from Slovakia. All these geological surveys, in addition to other activities, will be responsible for providing tetrahedrites found in their tailings, which will be used to manufacture those thermoelectric devices. Okay, well, but how did the idea for this project come up? What is the original spark? It's a curiosity, but I think it's nice or it's interesting to know. Okay, LENEG, in the LENEG, which is the Geological Survey of Portugal, there are 2 main departments: geology and energy. In the energy department, they were studying tetrahedrites as thermoelectric materials. It seems that one day during our lunch, in a relaxed atmosphere, materials engineers ran into geologists. The engineers were talking about tetrahedrites, but didn't know that Portugal has a lot of that mineral. The geologists told them that tetrahedrites are common, especially in some wet sites in the country. So you have these wet sites, which are an environmental issue, but they also contain a viable mineral, eureka. Let's move forward. Let's explore the potential, not just in Portugal, but also in Europe. And that's how the project started. Okay, following the presentation, and once we already know the project's primary aim, now it's time to figure out how to achieve this goal, the impact that the project can have on creating a more sustainable European Union, and how the project is organized to reach the main objective. So, how to achieve this goal? This goal will be achieved by using sulfides, mainly from the tetrahedrite mineral series, in the production of advanced P-type thermoelectric thermoelements. These tetrahedrites are found as environmental hazards in mine tailings and are collected in 5 European countries. As we told before, Austria, Spain, Portugal, Germany, and Slovakia, with the participation of the geological services from each country in the project. All these geological surveys, in addition to other activities, will be responsible for providing tetrahedrites found in their tailings, which will be used to manufacture those thermoelectric devices. Okay, the next step is to assess the impact that the STAR may have on creating a more sustainable and resilient European Union in 3 ways. You can see on the slide 1, 2, 3. First, it's reduce dependence on primary raw materials. Second, it promotes recycling and uses a common mineral to create value. And third, it produces thermoelectric systems that lower fossil fuel use, improve energy efficiency, and reduce greenhouse gas emission. So, to achieve its objectives, the STAR project is organized, as you can read on the slide, in 1 work package focused on coordination and management, 4 technical work packages focused on research, development, and innovation activities, 1 work package dealing with dissemination and communication actions, and one work package dedicated to definition of the innovation and exploration strategy. Okay, you can see in this slide the team project. Esther Boisereu is the team leader. She is a geologist, specialized in economic geology and mineral resources mapping. Concepción Fernández-Leyva, who is me, and I have the same field of specialization as Esther. Ramon Jimenez is a geologist and a mineralogist as well. He works in the museum in Madrid. Paula Adánez is my colleague who is presenting this work together. Is a geological engineer and a specialist in geochemical exploration. And finally, our colleague Jesus Reyes, who is a chemist and expert in mineral processing. Okay, what is the starting point? Green energy harvesting aims to supply electricity to electric or electronic system from an energy source present in the environment, for example, thermal energy, without grid connection or utilization of batteries. As we'll now see, almost all manufacturing processes ranging from steel to food production, for example, generate heat, what we know as waste heat, as do all machines from jet engines or microprocessors, for example. So the possibility of using thermoelectric devices to capture and to directly convert this waste heat into electric power is a very attractive and valuable approach to improve the overall energy efficiency and thus promotes a sustainable future. But what is the waste heat? For example, what kind of materials are suitable enough to use for making them? Let's see in the next part of the presentation. Okay, we will now review some essential ideas to understand the foundation of the START project, such as we have on the screen, for example, waste heat. Waste heat is heat that is produced by a machine, for example, or other process that use energy as a byproduct of doing work. Sources of waste heat include all manner of human activities, natural system, and all organisms, for example, air conditioning system, industrial processes, thermal power plant, etc., etc. Okay, in the picture on the right, we can see the temperatures that can be reached in some processes before mentioned, with the lowest temperatures, for example, associated with ventilation system or preheating warm water. We are talking about between 30, 70 Celsius degrees to the intermediate ones, joined with steam from steam generation plants. The temperature is between 100 and 275, or, for example, those processes that release large amounts of heat, such as fume in combustion processes or waste heat utilization for generation of electricity by steam processes. We can see the data at the top of the slide between 250, even 500 or 600 Celsius degrees. So very high temperatures. This picture is great because it's quite clear about the explanation what waste heat means in general terms. The picture shows that about 2/3 of the primary energy produced worldwide is lost as waste heat. So it's a huge amount. In the European Union, it is estimated that the potential for waste heat recovery could avoid tens of millions of tons of CO2 emissions. For example, this to illustrate what we have just discussed about waste heat, in this slide, I show you some of the results obtained in the Reuse Heat project. You can read on the top on the slide the name of this project. Founded by the European Union in the program Horizon 2020, the team have mapped European Union's urban waste heat potential. This is what is represented in this map with these points. As you can see, in some way, it displays all low-grade heat sources available in cities and includes also industrial waste heat and heat from waste incineration plants. So the legend on the left let us to identify colors with sources. For example, red is food retail, wastewater treatment plants in green, food production yellow, and so on. Okay, this is on the left on the legend. To see more detail, for example, an image from Spain, we have this picture, and the red and green points are clearly predominant in the map. You can see easily, which indicates that the most frequent sources of waste heat in Spain are associated to wastewater treatment plants, which were green, and food retail, which are in red color. So this is the predominant in the map, green and red points. Okay. Once we know what this kind of heat is, next we will explain what thermoelectric materials are and how they work. I mean, what characteristics they must have to be suitable for the manufacture of thermoelectric device. As I said before, the possibility of using thermoelectric device to capture and to directly convert this waste heat into electric power is a very attractive and valuable approach to improve the overall energy efficiency and thus promotes a sustainable future. Then the first thing is to know how a thermoelectric device operates and how it is designed. In this picture, in the right side, we can see how a thermoelectric device works by a thermal gradient between two thermoelectric materials that produce an electric field. This electric field is between the cold side and the hot side of each material. One of the materials is an N-type semiconductor in which most of the free charges are electrons, which means electrons are the main charge carriers, facilitating electrical conduction, and the other is a P-type semiconductor in which most of the free charges are holes, which means holes act as charge carriers, enabling electrical conduction. This is a bit tricky, but it's, I think it's, the picture is quite clear to understand what I just said. Okay, here it represents the efficiency of the thermoelectric material. So what I want you to make away from this figure is that the efficiency of a thermoelectric material is governed by its figure of merit, which you can read ZT, the blue line, which in turn depends on the Sepe coefficient with S, the electrical conductivity, sigma, the thermal conductivity with this K, and the temperature of operation. As we can see, semiconductor of those good conductors of electricity and poor of heat. And with this information now we are going to recap all the characteristics that a material should have to be considered a good thermoelectric material. Okay, this is the recap, the idea. So they allow waste heat to be converted into a source of energy. They convert a temperature difference into electricity. An efficient thermoelectric material must be a good electrical conductor and a poor thermal conductor. So in summary, we can say that there are few materials with these characteristics. In general, they are expensive, rare, or toxic. Okay. In this picture, we can see the materials currently used as thermoelectric materials. The color code of green, red, and yellow indicates the favorability of the material characteristics. Good thermoelectric materials have the figure of merit just above 1, and you can see in the first line, at certain temperatures. The best material are for commercial devices used at low to mid temperatures up to 500 Celsius degrees are based on telluride, like the first two columns you can see on the screen. However, there are environmental aspects to consider, such as toxicity, as well as other economic and political factors, including the following in the case of telluride technology. The main problems in Europe is tellurium is rare, and Europe relies on imports mainly from China, which produce over 60% of the whole production. The second important point is that manufacturing processes are often expensive and complicated. Then, tetrahedrite appears as a very interesting option, replacing telluride-based thermoelectric materials. Apart from favorable technological aspect, tetrahedrite is one of the most abundant sulfosal minerals in the earth crust. In this way, will reduce the demand for such a scarce commodity and will result in less demanding processing conditions. So these factors show why sustainable thermoelectric materials from tetrahedrite are important. So because the toxicity is not too high if you compare to the other one, environmental aspect is very common, is cheap to get, etc., etc. Okay, now it's time to talk about the mineral, the tetrahedrite. Well, the name is a tongue twister all the time. In Spanish, in English, it's tetrahedrite. So, tetrahedrite is a copper antimony sulfosyls that forms a complete solid solution with tennantite, in which antimony is replaced by arsenic. So, in the second part of the slide, you can read the different minerals belongs to the series, and the pure end members of the series are rarely or never seen in nature. The antimony-rich phase is the most common, and other elements also substitute the structure. We can enter in the structure mainly, for example, iron and zinc, along with the less common, for example, silver, mercury, and lead. Yes, bismuth also a substitute for the antimony, and bismuth tetrahedrite or anivite is a recognized variety. So there are, one of them are more common and the other ones, they are very rare. The related silver dominant mineral species like faberhita, although rare, is notable because it can contain up to, I think it's about 18% of silver. Okay. Okay, as I told you before, tetrahedrite is a very common mineral, and this map shows a selection of localities for tetrahedrite tennantite mineral series. As we can see, we can find all around the world. It is quite abundant, both in mineral deposit and in tailings, which is really, really important for our project. So, at first glance, it's great news for our project to know that it's an abundant mineral. Okay. In summary, the start concept, which is put in this picture, the main idea is to transform mining waste into waste heat recovery materials. This project is based on the idea, as I told before, green energy harvesting that aims to supply electricity to electric or electronic system from an energy source present in the environment without grid connection or utilization of batteries. Okay, it is important to highlight how IGME, in this case, because we are involved in the project, will contribute to the START project. As we know, IGME is specialized in geology and mining, so it has extensive experience in mineral resources research, mineral technology, and mining sustainability analysis. So, moreover, IGME has databases on mineral deposits and mining ponds and dams in the country. So, we manage a lot of information which will be very important in this project. What are our expectations? Well, our expectations are written on the screen, contribute to the complete life cycle of raw materials and processes, support national and Euro policies on raw materials and renewable energies, bring knowledge on future studies and exploitation of results, and use these results, the result in general of the project, to support the national mineral industry in the development of policies for these minerals in general. Okay. And now we will revise all the activities, because I'm focusing on the project itself, activities carried out by the Geological Survey of Spain in the START project. As you can read, we are participating in the work packages listed on the screen, as you can read easily, but this workshop is focused on work package 2. So we are involved in work package 1, focus on coordination and management, work package 2, selection of waste dams, separation and concentration, work package 4, materials characterization, work package 6, dissemination and communication, and finally the last one, which is work package 7, focus on innovation and exploitation strategy. Okay, this is the part of we are going to focus on in the work package 2. Okay, let's move on to, as I've told, work package 2, and as I told you before, we have two types of tasks in the field in this work package 2. Selecting the best tailings, and in the laboratory concentrating the tetrahedrites as pure as possible. In this way, the result of the work package 2 should be the delivery of as pure tetrahedrite as possible to the leaders of the next work package from the Spanish tailings. Let's take a look on the picture and the information that is present in it. As we know, or most of us, Spain is a country with a wide variety of lithologies and a complex geology, and in addition, it has a long and a strong mining tradition. For this reason, there is a high probability of finding tetrahedrite in Spanish territory. We are therefore in a position to select optimal mining waste site to supply these minerals to the START project. As you can see, the working plan has been divided into 3 main steps, plus data interpretation, the step 4, which is implemented at all stages. The step 1, the focus on the potential mining waste inventory. The second one, the field data collection campaign. The third one, field and laboratory characterization of the samples, and the fourth one, data interpretation, which is related to all the steps. Well, starting with the step 1, which has already been accomplished, was the creation of an inventory of sites with higher potential to find tetrahedrite in mining waste facilities. The first source of information consulted was our IGME's mineral resources database, together with the list of abandoned mining waste facilities. At this stage, there were 250 sites where tetrahedrite was mentioned. We started with a huge amount of points. A more accurate selection was made, keeping those points in which tetrahedrite appeared as the main mineral, because in the last one, tetrahedrite appear in different, not the principal mineral. So just taking into account where appear as the main mineral, we keep just with 50 sites selected. Eventually, the sites of interest were reduced according to other criteria, like the percentage of tetrahedrite in the mine waste sites, grain size of tetrahedrites, and volume of mine waste and their accessibility. So finally, we keep 21 sites were selected for the study. And on the map, you can see the 21 sites selected in different geological sites in Spain, geological settings. So Cantabrica zone, Australian zone, Osa Morena, etc., etc. Okay, the second step, it was field sampling campaign, as you can read on the screen. And the second step was the field sampling campaign, which we have already completed as well. At this stage, an in situ validation of the mining wastes was carried out. Validated sites are sampled and as well characterized in the countryside. From the 21 points selected in the last step, few have been definitely chosen to be sampled. Those with highest percentage of tetrahedrite larger grain size, and better tailing size. Okay, in this way, we eventually keep the best 5 sites, which are, as you can see on the screen, El Coriello and Mina Delfina in Asturias, Santísima Trinidad en Torres de Albarracín in Teruel, Sierrecilla in Huelva, and the last one in the south, Sierrecilla, and in the east-south is Lanteira in Granada. 5 places, 5 sites. Okay, in each of the selected areas, we have provided a brief summary of the main characteristics related to the geological context, type of ore, paragenesis, etc. So for the first one, which is Delfina, is in Asturias, as I told you, and as you can see on the screen. It's in the Cantabria Cordillera, and the deposit type is a low temperature hydrothermal deposit in the Carboniferous limestone of Picos de Europa formation, and the mineralization is in subvertical veins and veins, generally in a northwest-southeast direction, as well as in irregular masses filling karst cavities. In this case, the paragenesis pyrite, chalcopyrite, and tetrahydrotenantite with abundant secondary minerals like limonite and copper, carbonates, and so on. You can read the secondary minerals. And the volume of the waste was 600 square meters. And the material sample was about 25 kilos. The second place was in the same geological setting in the Cantabria Cordillera, is El Coriello in Asturias as well. The deposit type is low temperature hydrothermal deposit, and the mineralization is found in quartz veins included in the Montaña limestone from the upper Carboniferous. The paragenesis is tetrahydrite and quartz with occasional copper carbonates like azurite and malachite. The volume of weight, it was 5,000 square meters. In general, the tailings are small, although they contain abundant fragment of vein quartz with tetrahydrite, so the concentration is high. And the material sample was 50 kilos. More or less. This is the amount. Okay, the third place was Santísima Trinidad mine in the Iberic Cordillera. The mineralization has a vein morphology trending east-west. The paragenesis was galene and tetrahydrite with abundant siderate with quartz and calcite. The volume of waste, it was about 6,000 square meters, although there are other mines nearby, so this place is quite interesting, and the material sample was 40 kilos. The fourth one is Sierrecilla mine. It's in the Iberian Pyrite Belt in the south of Spain, in the west side. The deposit type is VMS type deposit, and the paragenesis is sphalerite, galene, tetrahydrite, chalcopyrite, and pyrite. In this case, the volume of weight, it was 4,000 square meters, but the problem in this way is that the grain site is really small. We can see the site, so very difficult to separate where, as we are going to check in the laboratory, and Paula is going to talk. And the material sample is 35 kilos. And finally, the last place is El Vagón Mine in Lanteira, in Granada. It is in the betics, the geological setting. The deposit type is tetrahedrite, is found in veins with maximum length of 80 to 10 meters and thickness that usually do not exceed this long or numbers, although they can exceptionally reach up to 5 meters. The paragenesis is copper sulfides and sulfosalts with chalcopyrite and tetrahydrite with siderite as gangs. Is a very, very common, this gang. The volume of weight is 2,000 square meter, and the material sample is 20 kilos. So next, I'll hand it over to my colleague Paula to continue with the presentation and focus on the laboratory and separation process. Okay, thank you very much.
Thank you, Concha. Can I share my screen? Okay.
Yes, thank you, Concha, for your presentation. We will continue with the next lecturer, Paula Adánez. She holds a PhD in mineral resources, materials, and energy, and environmental engineering from Mining Engineering School, Politécnica, University of Madrid. And she is a senior specialized at the Geological Survey of Spain, IGME-CSIC, in the Department of Geological Resources for Ecological Transition. Her work has focused on research projects of mining potentiality, as well as projects related to the reuse of raw materials in abandoned mining waste facilities, the two main lines of research being mining exploration and environmental geochemistry. She is currently involved in several international competitive projects and national projects too in the field of primary and secondary mineral resources. She's a member of the steering committee in the Commission of Global Geochemical Baseline of the International Union of Geological Science. She's a representative of IGME-CSIC in the geochemistry expert group in Eurogeosurveys and in the expert group of geochemistry in ASME too. Paula, you can start your presentation whenever you want.
Thank you. Thank you, Virginia. Can you see the presentation?
Yes.
Okay. Okay, so Concha has already explained the two first steps followed in our work package 2, with where the IGME is collaborating. And now I will explain the step 3, which is the work that we have done in the laboratory with the essays aimed to concentrate the tetrahedrite. The final objective of the project is to supply tetrahedrite concentrates in sufficient quantity to carry out a thermoelectric test on these materials, which is the objective of other work packages of the project, as Concha has already explained too. The aim of this step 3 is to test the best methodology in order to obtain a single mineral concentrate from a waste dump. This mineral is the tetrahedrite, which is scarce in the waste dumps, and it must be separated from other minerals that can be found in these facilities. Due to its characteristics and the characteristics of the gangue, several tests have been carried out. So the general protocol followed is the one here in the screen. First, we have made a mineral characterization, then the sample preparation, a mineral separation test of and concentration of the tetrahedrite, and then a final chemical characterization. A first mineral characterization, as I have said, has been carried out in small representative subsamples of all the samples that we took in the field, in order to decide whether it is worth or not to include each of the 5 sites selected in the study of the laboratory. With this objective, we have made polished sections and thin sections from hand specimens. We have also studied material that have been previously ground. And we have observed and analyzed these samples through the optical microscope, the stereo microscope, and the scanning electron microscope. And finally, we have made a final selection of the sites that will be included in the laboratory essays. In the first of the sites, the Delfina mine in Asturias, we have observed mainly calcite, tyrolite, minerals of the tetrahedrite tenantite series, pyrite, chalcopyrite, and quartz. The main gangue here is calcite and a little quartz too, together with tyrolite and other sulfides. The average grain size here is classified as medium, as it is bigger than 63 micrometers. And with the aid of the microanalysis in the SEM, we have seen that the antimony contents are much lower than the arsenic contents. So here, what we have is mostly tenantite. We have decided to include these sites in the study. In El Coriello, we have observed that the main minerals present in the samples are tetrahedrite, malachite, azurite, and quartz. Here, the main gangue is quartz and copper carbonates. The grain size is also here considered as medium, and in the analysis, it has been observed higher contents of antimony than arsenic, so we have mainly tetrahedrite here. We have also decided to include this site in the laboratory essays. In the Sierrecilla mine, the observed minerals are mainly sphalerite, galena, tetrahedrite, chalcopyrite, and pyrite. Here, the grain size, as Concha has already mentioned, is very fine, with less than 63 micrometers. We can observe this grain size in the images taken through the microscope. And here we have also mainly tetrahedrite. Due to this fine grain size, we have decided not to include this site in the study because grain sizes smaller than 63 micrometers would need other procedures, for example, flotation, where other chemicals are needed. These processes are more expensive and time-consuming, and also they are usually more complex. So this will not be included in the laboratory essays. In Torres de Albarracín, it has been observed that the main minerals present in the samples are siderite, accompanied by tetrahedrite, galena, and quartz. The main gangue here is siderite, which accounts for more than 80% of the whole sample, plus quartz and other sulfides that are mainly galena. The grain size here is medium, and antimony content is higher than arsenic content, so here we have also tetrahedrite as the main mineral. This site has also been selected for the study. And finally, in La Inteira, the observed minerals have been copper sulfides and sulfosides, where chalcopyrite and tetrahedrite are the predominant ones, and also siderite is present. The main gangue is quartz, siderite, and other sulfides, and the grain size is also here medium. Tetrahedrite is the main mineral too, and we have selected also this site for the study. So from the 5 sites pre-selected for the study and that were sampled in the field, we have finally selected 4 of them for the laboratory essays. The main parameter regarding the selection has been the grain size. With a fine grain size, as I have said, chemical separation methods would have been necessary, as these methods require a number of precautions in addition to the disposal of hazardous wastes. It is not within the objectives of the project, which aims, among other things, at sustainable to create or to get a sustainable product. Another important parameter that has to be taken into account is the content or not of siderite. It is important because, as I will explain later, the presence of this mineral will decide the type of process to be followed in the laboratory. So we have the Delfina mine, where we took, as Concha has said, 25 kilograms, and Coriayu mine, where we took 50 kilograms, and none of them had siderite in the paragenesis. And on the other hand, we have Torres de Albarracín with 40 kilograms sampled, and Lanteira with 20 kilograms. Both of them having siderite that will be treated as a gangue. And here we have a diagram of the procedures that we have followed in the laboratory. The first part has already been explained with the characterization and the final selection of the sites to be studied. And for the next steps, first of all, we made a previous separation of the samples with a grinding and sieving of the material. And the next steps depended on the paragenesis of each of the sites. We have 2 facilities where the siderite was present and usually in big quantities, and we have 2 other facilities where there was no siderite. The procedure followed to concentrate the tetrahedrite is not completely the same, although it's similar in the 2 cases. And now we will see all the steps that we have followed in both cases. First of all, and in both types of ores, we have to prepare the sample in order to be able to make the separation of the minerals. The first step is grinding the material. Here we have taken, in the field, we have taken samples of fragments of around 1 or 2 to, for example, 10 centimeters. And now we have to grind all the material to less than 1 millimeter. We have used, for this purpose, wheel or roller mills. And once the sample has been ground, we have shifted to mesh sizes of 1 millimeter, 500 micrometers, 250 micrometers, 125 micrometers, and finally 63 micrometers. The sample that was bigger than 1 millimeter was again ground, but in a smaller mill, of course. We had to be careful as well not to ground the sample in excess. The danger here is to generate fine mineral that will not be useful and has to be discarded because it cannot be included in the laboratory assays. And here it is important to insist that it is better to grind the sample several times for a short period of time and then sieve all this ground material than to grind all the samples to less than 1 millimeter just in one time, because that way we would generate much more fine material that should be discarded and will be lost. But the most important thing, the most important thing here is to study which is the liberation size that we want to use in the assay. So apart from grinding to less than 1 millimeter, we try to get more material of the fraction with that liberation size. So during the grinding and sieving, the grains are always observed through the stereo microscope, and the liberation size is then decided. In our essays, it has been observed that for all the samples, the liberation size was the one lower than 500 micrometers. And here, I want to make a small remark in order to make clear that the study of the liberation size is one of the most important things for any mineralogical process. The classical definition of mineral liberation shows that in a population of particles of different mineral species, the degree of liberation of one of the species consists of the percentage of this mineral which occurs as free particles in relation to the total amount of this mineral in mixed or free particles. So the liberation size is the grain size that we need to reach for all the ore to be freed, so that the ore grains contain only one mineral ore. Here we have an example of the usual aspects in the left of the screen. These the usual aspects of the grain, and here in the right, here is a grain containing only one mineral. This is an ideal case. It is impossible that all the grains are liberated, but the liberation size is decided regarding the grain fraction with a higher percentage of grains with liberated minerals. It is also important to note, that in this study and in all waste dumps in general, we have the advantage that the ore is already mined and partially milled. So this means that the energy consumption is reduced. And so once we have the samples ground and sieved at the different grain sizes, we move on to the next step. As I have explained, there is a difference in the treatment of the samples depending on the minerals that are present. If we have a gangue without siderite, which is the case of Delfina and Coriayu mines, we have followed 3 steps that are: first, a delamination, that is the washing of the finest material in order not to influence in the rest of the separation process. After drying, we have done a density separation with the Whiffley table, where sulfides are separated from the quartz and other light minerals. And finally, after drying, we have done a magnetic separation with the France electromagnetic separator, where the tetrahedrite is separated in the magnetic fraction. And in the case of the samples with a gangue rich in siderite, which are the Lanteira and Torres de Albarracín sites, there is one more step that had to be added to the general procedure. After the lamination is where we added this supplementary step. We found a big problem in separating the tetrahedrite from siderite. Both of them are magnetic, but in different intensities, but the great percentage of siderite made it quite time-consuming to treat all the sample through the France separator. So after several extra essays, we got to the conclusion that the best method was to introduce the sample into a permanent magnet that is located, in particular the one that we have used in the School of Mining Engineering of Madrid. And here in a magnetic field of 0.3 amperes, the siderite was separated from the rest of the sample. The following steps are the sample as in the case of the samples without siderite. That is a density separation with the Whiffley table, and here a second magnetic separation, this time with the France electromagnetic separator. As I have explained, the first step, which is common to both kind of samples, once we have prepared the samples, is the delamination. It is the first step before in the separation process. The sample here is washed through a sieve of 63 micrometers. We did it by hand. Here in the photograph, we can see the process. We did it by hand, but there exist other laboratory methods. The discarded material are the fines that were produced during the grinding of the samples, but were not sieved. It is important to eliminate this material, as it would affect the magnetic properties of the rest of the minerals. Finally, the delaminated sample has to be dried in order to carry out the next steps. The following step must only be applied to the samples with a gangue rich in siderite. A permanent magnet is the equipment, as I have mentioned, that we have used. It consists of a band with a permanent magnetic roll made of rare elements with an intensity of 0.3 amperes. Here we have a diagram of the way it works. The band is fed with the material. This material travels with the conveyor belt, and at the end there is a roll where the magnets are placed. So the magnetic material is attracted to the magnets and remain attached for a longer distance. The non-magnetic material falls first and is collected in a tray, and while the magnetic material falls later and is collected in a different tray with the aid of a splitter. The velocity of the material feeding and the band can be here controlled. And here we have some photographs of our work. As I have said, siderite and tetrahedrite are both magnetic minerals, but at 0.3 amperes, siderite is separated in the magnetic fraction, and tetrahedrite goes with the non or light magnetic fraction. It is recommended, as we can see here in the photograph, is recommended to leave a thin layer of material so that all the grains can be attracted by contact to the magnet, which is placed here. So what we have after this procedure is a magnetic fraction, which is really pure siderite, and the non-magnetic fraction, which is the tetrahedrite together with galena and other sulfides, plus quartz and other gangue material. The non-magnetic fraction is passed back again in order to make a purer fraction. In our case, we repeated this process 3 times. The following step is applied in both types of samples. It is the separation by density difference of the minerals, and here the Whiffley table is the equipment that was used. With a combination of vibration, water flow, and inclination of the table, the material is separated between dense material and light materials. In the denser fraction, we will have the tetrahedrite and other sulfides, and in the light fraction, we will have the quartz, calcite, and other gangue materials. It is very important also to wash the dense fraction with ethylic alcohol after the separation and before drying this concentrate in order to avoid the formation of oxides. Here in the photographs, we can see very easily how the minerals are separated because there is a big difference of color between the dense fraction and the light fraction. The next step is the magnetic separation, and it has to be followed in both cases or in both type of sites. To carry out this separation, we use the Franz electromagnetic separator. The dense fraction from the Whiffley table has to be previously dried, of course. The Franz produces a strong magnetic field over a ramp that holds magnetically susceptible material, while non-magnetic material falls to a second ramp. Here we have a diagram of the different parts of the equipment. We can control the angle of the ramp and the strength of the magnetic field. I think it's here. And we can also modulate the flow of the material that is fed and the vibration. The material goes through the ramp, and the high magnetic fraction is collected in one tray, while the low magnetic fraction is collected in a second tray. In our essays, the purest tetrahedrite was obtained at 0.7 amperes. The non or light magnetic fraction was passed back again to make a purer fraction, and this procedure was repeated at least 3 times. Here we can see the difference in color and the difference in color of the magnetic magnetic and non-magnetic mineral. Here would be the tetrahedrite concentrate, and this would be the final product of the tetrahedrite concentrate. The final procedure was to analyze the concentrates in order to make sure that we had a pure tetrahedrite. For this purpose, we used the X-ray fluorescence for a semi-quantitative measurement of the elements present in the concentrate. Here we could see if the presence of antimony, arsenic, iron, or copper, for example, were in agreement with a concentrate of tetrahedrite. We also used the X-ray diffraction for a semi-quantitative measurement of the minerals that are present in the concentrate. Here we could verify if the tetrahedrite was so pure as we wanted in the concentrate. So what we finally got was 1.2 kilograms in Delfina mine of the concentrate of tenantate in this case, 4 kilograms in El Coriayu mine, plus other 3 kilograms that was processed in a second sampling campaign. We collected 350 grams in Torres de Albarracín and 155 grams in Lanteira. All of these concentrates have a purity of at least 95% of tetrahedrite. With all the information, we are now making a valorization of the concentration process in the different cases that we have tested. There are important parameters to be taken into account in order to assess the reproducibility of the process in an industrial scale. And they are, for example, the quantity of water consumption during the delamination and the density separation in the Whiffley table, the energy consumption during the drying and the magnetic separation. The time consumption is also very important, and the use of chemicals that have to be treated separately. The type of mineralization is also essential in the valorization of the process. So we have here a comparison between the two types of mineralization that have been used for the assays. And with this, we can say that the water consumption is similar in both types of ores. The energy consumption is also similar, although a bit higher in the case of the ores reaching siderite, obviously because it has one more step. The use of contaminants is in both cases very low. Time consumption is higher in the case with the gangue reaching siderite. And finally, regarding the final product, we have got a bigger percentage of the tetrahedrite in the cases where there was no siderite. But in contrast, we can say that we got a very pure siderite with the magnetic separation, so it could be used as a byproduct, so it could increment the value of this type of ores. So finally, as conclusions of all the work that has been explained, it can be said that Spain has a great potential in tetrahedrite deposits for thermoelectric uses. 250 deposits with tetrahedrite were detected, and 50 of which the tetrahedrite was the main mineral. 21 deposits were selected for a more detailed study. Then 5 waste dumps have been sampled: El Coriayu, Delfina, Sierrecilla, Torres de Albarracín, and Lanteira. And finally, 4 sites have been tested with the laboratory assays. The waste dumps that have proved to be the best for obtaining tetrahedrite concentrates are those where the tetrahedrite has an average size greater than 63 micrometers, the paragenesis of the ore is simple with low contents of sulfides, and the one with a gangue where the gangue is mainly quartz and without siderite. It has been proved that the tetrahedrite can be concentrated with just physical procedures, avoiding the use of contaminant substances. Now, regarding all the project, different protocols have been followed in the different laboratories from the different countries of the rest of the participants, but conclusions are very similar, and all the laboratories have been able to concentrate tetrahedrite with physical procedures. So we can say that we have proved that the tetrahedrite has really a great potential as a sustainable thermoelectric material. And this is all. Thank you very much. If you are interested in the project, you can follow us on the social media.
Thank you so much, Paula. It has been a very interesting information. I see that there is no question in the chat. Okay, there is one. Joanna Butlanza says, sampling was only superficial. Did you see any change in the tetrahedrite with depth of the deposit?
Can I answer, or Concha? Maybe
Whatever
we
you
have
want.
not made it clear, but the sampling has been made only in the waste dumps. So we have only sampled the material that was on the surface and that was already mined, and it was just wastes.
Okay, thank you. Does anyone else have a question for Concha or Paula? Well, I guess we can continue with the next presentation. Thank you, Paula and Concha again very much for your time and your presentation, your interest presentation.
Thank you.
Thank you.
Thank you very much. Bye.
Bye. We continue with our next speaker, Ana Patricia Pérez Fortes. She will speak about reuse of mining waste in the manufacturing of sustainable construction materials. Ana Patricia Pérez Fortes, PhD, is an associate professor at the Universidad Politécnica de Madrid, specializing in geology, rock mechanics, and the application of mining waste in sustainable construction materials. She has a background in civil engineering, and she's a member of the Centro de Investigación en Materiales Estructurales and the research group Tecnología de la Construcción y Ciencia de los Materiales para la Edificación y la Obra Civil. She has also done 2 research stays at Norway and 1 research stay at Portugal. Her research primarily focuses on the development of innovative, low-impact construction materials, integrating technologies like virtual reality and 3D modeling to enhance the technology of geological science. Her contributions to sustainable infrastructure include investigating the durability of aggregates used in roads under extreme conditions and exploring the potential of the alternative materials for more eco-friendly construction practices. Additionally, she has participated in some projects related to urban sustainability and digital innovation in construction. Patricia, we can start your presentation.
Okay. Hello. Thank you, Virginia. Can you listen? Can you listen me?
Yes.
Yeah. Okay. Yeah. So thank you so much for your introduction. I'm going to start with my presentation. We are going to make here a review about the use of mining waste to produce construction materials. So, well, I will try to be fast and to try to resume this topic, but because it's a general topic. So, but first of all, I think we must talk about some numbers and some concepts to understand why we try to reuse these materials in construction. So, well, now we go with the numbers. Well, in the future, it is estimated that we are going to use more than the 300% of the materials that the Earth is able to produce. So that's why we need to stop this and to try to go to more sustainable production systems. Also, specifically, the construction sector is responsible of the 50% of the natural resources used in the planet, and also is responsible of the 50% of the total waste that we generated in the earth. Also, these numbers are from almost 15 years ago. We can see here in this graph a projection about the use of these construction materials in the future up to 2060. So we can see that we are going to double the use of these construction materials, especially sand, gravel, and crushed rocks, followed up by metals. It's not the case of crude oils, and we will see why in future slides. At least we are going to stop to use these crude oils. Well, we can see also two graphs where we can see the evolution of the use of the construction materials in different regions. Also, we can see in Europe we trended to reduce the use of materials. They are other emerging countries like China or India that have almost double the demanding of these construction materials in last years. So that's why we need also to think about possible solutions to this material demanding. Well, in this graph, we can also see what are the construction materials that we are demanding. We can see in purple that concrete is the most demanded construction materials, and you can see that the scale we're talking about is billions of tons of materials. So in 2017, 2017. We used almost 8 billion tons of concrete, and concrete is followed up by aggregates used for another uses, not for concrete, that you can see in dark blue, and for bricks. And also we can see we have to have in mind that we use aggregates in concrete and aggregates for other purposes, because concrete is formed by aggregates, water, and cement. Specifically for concrete, concrete is the responsible of the 8% of the global CO2 emissions. These data are from 2020. And annually, the production and consumption of concrete is responsible of 4 billion of tons of CO2 emissions. So that's why we also must think about how to design more environmental friendly materials. Well, with these considerations, with these previous considerations, at the end, the production of construction materials and the use of these materials suppose the consumption of energy in all its stage, from extraction, production, transportation and construction, and the final use of the material. It demands also raw materials, of course, to produce the construction materials, water, fossil fuel, and other materials and chemical products. Okay, this the production and use of material constructions need and demand these materials and resources, but also it has an environmental impact on the climate, on soils, on human health, and other questions. On the other side, if we speak about raw materials related not with non-metallics, because we have in construction materials, we used to work with non-metallics materials, but in case of metallic materials, here I show you a graph made by the European Commission about the supply risk of metals. Because more and more metals are gaining more importance due to they appear in all the industries, the net zero industry, digital industry, aerospace, and defense sectors. So now all the new industries need these metals. So European Commission classified the metals from very low to very high supply risk. That means that European Union is not able to produce by itself of these materials. And you can see here in red that these materials are directly related with renewable energies. So this is another debate, but I think it's so interesting to see if these renewable energies are really clean or no. So, but this is another question and another presentation, because at the end, in the future, we are going to demand more and more metals. That means we are going to demand more and more mining activities that are going to produce more mining waste. And that's why we try to use this mining waste in construction. And this is, okay. Also, we need to think about the environmental impact of this mineral production that we have seen that is going to be more and more important in the future. So this mineral production will require energy, land, water, and chemicals to produce the minerals we need for these industries. Of course, we will produce the minerals that we need, but we'll produce also some waste. This waste and the use of the reserves that we need to produce these mineral productions have these environmental impacts on water, soil, biodiversity, and climate. So that's why we need to think about what to do with this waste and what to do with this material construction demanding. Well, in this context, as I said before, we need to think about production and consumption systems that must be inside the limits of our planet. And that's why the United Nations in 2015 proposed these sustainable development goals. When we think about reused materials, we think about the 12th point. This 12th point is related with responsible consumption and production. But when we speak about the use of materials in another industry, we can talk also about the point 9, industry, innovation and infrastructure. Also points 13, climate action. We are going to improve or try to improve the life below and on land, below water and on land. And we were trying to keep clean water and sanitation. Anyway, we are going to focus this presentation in point 12, responsible consumption and production of the materials. And within this point, we need to talk about another concept that I'm sure you know, I'm really sure. It's circular economy. At the end, we want to recycle and reuse the materials, the existing materials, trying to creating a new an added value for them, and try to revalorize it and revalorize these the materials. So at the end, we want to close this wheel. From the raw materials, we need to try to think about how to produce and collect and recycle these materials, trying to don't generate or reduce the generation of residual waste. Well, also we need to think how to treat the waste and how to treat the materials and how to decide them. And that's why we need to think or we need to know about this waste hierarchy. This waste hierarchy is organized from least desirable to the most desirable processes. So, of course, the most desirable process is reduce the use of materials in construction. So we could try to design infrastructures and buildings, trying to use as less as material as we can, and also make durable materials, trying to keep these products for longer. Follow this the reduce of the raw materials. We can reuse the materials. That means just clean, repair the material and use it again. And in the middle of the hierarchy, we can see the step recycle. So we are going to talk about recycle in the whole presentation, because we are going to turn waste from mining into a new material that we can use on construction. So I think this is the most important concept maybe here, but sometimes also we can choose some recovery process. That means that we can treat the waste to try to use to reuse it in the future. So in construction materials, mining waste can be reused, recycled, or recovered. Of course, what we don't want to do is to dispose the waste in landfills and to incinerate them. This is the least desirable. So we are going to explain more or less the 3 steps in this presentation. Well, now that we have seen the context and the environmental impact of construction materials and mining industry, we need to think about how to design sustainable construction materials. Well, the most important parameters that we have in mind when we design a construction material is that it has to have it must have some or meet some structural criteria, because construction materials in general, they are going to support all the loads of the infrastructure of the building. So they must have some structural properties that we cannot avoid. Of course, we demand billions of tons of construction materials, so they must be economical. So the cost is very important in this field, and we should try to especially in infrastructure, to build a long life service infrastructure. So the material must be durable. With this parameter, structural properties, cost, and life service, we need to think how to design our construction material. Now we have to incorporate the environmental context of construction materials. First, and in this presentation, we are going to focus in this first point. We need to think about the use of the raw materials. What are the materials that we are going to use when we want to create this construction material? So we can choose low environmental impact materials, and also we can reduce the raw materials we need, such as the use of cement. Also, we can try to design a production processes energy with energy efficiency, thinking about low carbon processes, or to use renewable energies. As I said before, we want durable infrastructures, so we want long service life infrastructures, and also we want materials resistant to degradation, because these avoid future maintenance and repair operations. We also can think about the end of life of the material, if it's recyclable or not. For example, it's so common now, the use of the demolition waste in the production of new construction materials. And we must think about of course, the circular economy concept when we design this construction material. Again, during the life, the service life of the material, we need to think about the life cycle assessment, the embodied carbon, and maybe we can try to use alternative binders to cement that produce almost the 8% of the CO2 globally emissions. Also, we should try to minimize the water consumption or try to recycle water during construction materials production. And at the end, especially for buildings, we need to create construction materials healthy and environmentally safe. That means not toxic materials. I suppose nobody wants to access to a building with heavy metals, for example, in the walls. That's why we try to use natural materials as if it's possible. And especially for buildings, it's also very important the thermal performance of the construction material, because it can reduce the use of heaters and coolers in winter or summer. So especially in buildings, this is so important. As I said before, we are going to focus this presentation in the use of raw materials and how to use materials that can reduce the environmental impact of these construction materials, and try to reduce the non-renewable resources such as the aggregates or cement. The way to do it is going to be in some case the reuse of materials, but in most cases it's going to be the recycling of the materials. That means the adaptation of the material to of the waste to be used in another new product. And in other ways, less desirable, we are going to think to speak about the recovery of the materials. That means materials that need to be calcinated, for example, that requires energy. In this review of mining waste, first we need to think about from where we obtain what is the origin of this mining waste. The origin can be the surface mining, as you can see here in this scheme. Surface mining produced waste rocks, of course, and landfill waste. On the other side, we have the underground mining, and this mining produced also landscape waste, landfill waste, and also tailings ponds that are this. This is similar to a pool with a slurry inside. We will see after what's that. So we are going to explain in this presentation the use of these waste rocks, the landfill waste, and tailings in construction. So I think the most easy use is the use of rock waste from quarries. So here you can see a granite quarry from Iran. So in this quarry they produced ornamental or natural stone. They cut, here you can see the cuts. They cut these blocks to be used as blocks in pavements, for example, or in buildings. So of course the blocks that they sell are this one, but you have this another blocks, irregular blocks that cannot be sold. So these blocks can be crushed and used directly as aggregates on roads, on pavements, and other layers of roads, in railways as ballast, or in concrete. So this is the easiest way to reuse a material. Is easy. So here you have an example of the reuse of another granite quarry. Well, the picture is not so beautiful of the grave, but you can see the use of this ornamental granite and the granite wastes, and they crushed the granites in different grain size for ballast. This is the ballast. This is the aggregate used in railways. They can reduce the grain size, the particle size, and they can use it for concrete. So this is another. This is a really easy way to of circular economy. Well, from surface mining, from this kind of quarries, when you cut the stone, you produce this sludge, and these sludge are formed by thin, fine or coarse particles of rock. So these small particles of stone can be used to replace partially the cement or as filler if they are enough thin, less than 63 microns. Combined with clays, they can be used also in bricks and pavers. They are called eco bricks. Again, if they are enough thin, they can be used as filler in asphalt, concrete, or ceramics. After thermal processing, this is a recovery process because we demand energy. They can be used as lightweight aggregates. These lightweight aggregates has a really low density, and they used to be used in high buildings. Or for thermal and noise insulation. We can use it if the stone is rich in alumina and silica. They can be used also as alternative binder. In this way, they are called geopolymers, and we will talk about this in next slides. Well, as I said before, on surface and underground mining, we produce also landfill waste. We have the ore deposit. This is a coal mine. The machine now is extracting the coal deposit now, and all this material is soil, gravel and sand that that must be removed to stabilize the faces of the mine. So this landfill waste can be used directly without any treatment in bases and sub-bases layers on roads, as foundational fill materials, also for landscaping if they are enough coarse, or I don't know if you have seen in some on the sides of the road these hills. These hills can be artificial, and they used to be noise barriers. They avoid the noise to the sides of the road. So this is another example of the reuse of waste, mining waste. And this is also another simple way to reuse this material. More complicated is the reuse of tailings. As I said before, tailings is a common byproduct. generated during the extraction of metals or another or minerals. They are usually liquid slurry. So in the first stage, we extract the material, as our colleagues said before. So we must separate the ore deposit or the ore mineral from the gangue. Once we have the desired mineral is extracted, we produce this slurry that is stocked in these tailings. There are different ways to design tailings, but in this example, we can see the materials that we use to produce design these tailings, to construct it, to build them. So we have this dike. This dike avoid the slide of the tailing material, and we have water on the top. Of course, we can also have dry tailings, but the most common is to have humid tailings. And we have another dike, and the slurry from the extraction plant, from the processing plant, is expelled to the tailing, and the water is discharged on the opposite. And there's a small dike also to try to storage this water. As you can see, there can be infiltration of water to the ground. So, of course, mine tailings have a health and environmental impact on the earth. So they have a negative impact on soil. They produce dust if they are dry, because the wine can pick up the small particles of tailing and to transport to nearby communities. They have a negative also impact in water due to heavy metals leaching, or even also due to the infiltration of the water in the ground. The most catastrophic, maybe the most known process are landslides due to the unstable the instability of tailing piles, causing of course a disaster. And we never think about the land use because the tailings ponds needs a really huge surface that cannot be used for farming or for to cultivate anything. Well, that's why it's getting more and more important to revalorize the materials from these tailings. So from the point of view of the life cycle of mining industry, we can see that we have the open pit or the mine. We extract the ore deposit, we concentrate it, and we obtain the desirable metal. During this process, we produce these tailings, and the material from these tailings can be used by the proper mine for their activities, but they used to be storage in tailings. And that's why we need to reprocess, reuse, and revalorize this material. And why we can do it? How we can do it? Well, with using them in construction materials. Well, before to understand why we use tailings in construction materials, we need to think that we have two different types of materials. The coarser, that is these fine fraction sands, and the smallest that has a particle size less than 75 microns, that is this fine fraction slimes. So regarding these both types of material, we are going to use them in a way or in another way. In general, we are going to use them in similar construction materials, but in a different way. Well, in case of the sands, due to their size, they can be used to replace fine aggregates from concrete. That means that we can try to reduce the use of sand in concrete. Also, if they are small, we can use them also as filler. In road construction, they can be used as filler also in asphalts or in subbase and base layers. They can be used also as raw materials to produce bricks and blocks and paving stones. And also they can be used as binders, as geopolymers and alkali activated materials. As I said before, if they are rich in alumina and silica, they can react with water and cement. They can react with water in a similar way to cement, and we can reduce the use of this binder in concrete. Also, they can have regarding the composition alkali activated properties. That means puzzolanic properties. Also, they can be used in grouts and injection materials. That means that we can fill voids in stones, in tunnels, etc. We can also improve the stabilization of soils combining these materials with binders, and they can be used also in ceramics, tiles, or in other fire clay products as raw materials, more related with the use of sands in this case. And they can be used also in the top layer in landfill applications when we need to prepare this, for example, these noise barriers on the sides on the road, and also in green infrastructures and landscaping, because they have drainage properties, so they can improve the moisture content and behavior of the soil, and they also can help to control the erosion of this kind of green infrastructures. In the case of fine fraction, the slimes, they have a special size and composition. So before to use them in construction materials, we need to make some considerations. The most important considerations is that these materials must be chemically stable and environmentally safe. That means that they must not have heavy metals. And also, usually these materials require processing, such as the watering or chemical stabilization, to be suitable. So this is what we said about these recovering processes that are less desirable because they require energy and another materials consumption. Similar to sand fraction, slimes can be used to replace, to partially replace the cement or as a reactive filler in cements. As a geopolymer binder, it can be used as a primary or secondary component of these binders. Also, it can be used as filler in concrete and mortar. This filler, I didn't say it before, but the filler is commonly used to improve the resistance and durability of concrete and asphalt. Also, it can be as binder in weak soils to improve to stabilize the soils. And in this case, these slimes has impermeability properties, not permeability properties like the sands. If properly processed and free of contaminants, they can be used or used also in asphalt mixtures. They can replace the clays that we used in bricks and tiles. We can use them also to cover and to fill these voids in stone and tunnels and etc. But in this case, they are ultra fine fillers, so they can be used in smaller in smaller voids, and they can be used also in sealing layers in landfills or ponds, or in erosion control of this green landscape. Another special use of these slimes is in self-compacting concrete. This concrete must be more fluid than the usual, so these slimes improve the flowability and reduce the water demand of this kind of concrete. And they can be used in another green construction materials like eco blocks, or with composite materials. They can be used in plastic composites or low energy construction panels. So as you can see, they can be used in several ways in construction materials. Here there's an example of the use of these tailings in concrete. So from different tailings of different mines, from copper, boron, gold, we obtain the core size, the aggregate, that we can partially replace the sand of our concrete. And also from the slime, we can replace part of the cement that used in this concrete. And here there are some relations between the composition of the tailings with the compressive strength, with the resistance of the concrete. The highest content of alumina and silica, of course, will produce more resistant concrete. And also the relation between the maximum particle size with the compressive strength of the concrete. Well, again, we need to think about that if we are going to use construction materials, they must have some structural properties. That means that they must meet some quality criteria. Also, we need to produce economical materials and durable. The quality and economic requirements, of course, vary. Is different regarding the use of the mining waste and the final use of the product that we are going to use. Here I show you the easiest example of reuse of mining waste, that is the use, for example, as aggregate. So we can take a mining waste and use this waste as aggregate. More than almost concrete and asphalt mixtures are formed by aggregates. So aggregates must be abundant, low cost, and resistant and durable. So if we are going to use mining waste, we need to check if they are abundant, if they are economical, the cost of the use of this mining waste in our infrastructure, and the resistance and durability of the final product. Okay. As we've seen before, they are abundant, so there's no problem with that. But maybe there's some problems because we need to process this mining waste, so the cost of the material will increase. Also, regarding the composition of the mining waste, we can have some problems about the resistance and the durability of the final construction of the final product. So that's why when we design a construction material regarding the environmental aspect, we need to make a balance between the environmental benefits we obtain producing this material and the properties of the end product and the cost of the production of this new construction material. So to make a summary, we have a wide variety of mining waste available from surface and underground mining, but we need to make some considerations before to applicate it to produce construction materials. And it's their abundance, the economy, if the production is low cost or not, it will increase the cost or not, and the product properties of the final product. And we must check the advantage and disadvantage of using these materials. At the end, we will obtain a final product, and of course, the quality of the final product should not be never and ever compromised. And that's why, in general, the use of this reused material, mining material, is limited. So we just only partial replace the raw materials for these new waste materials. And well, as I said before, we can use mining waste in a lot of construction applications, and they offer, of course, benefits because they are abundant, and they reduce the need of virgin raw materials like aggregates or cement. Of course, they contribute to circular economy. We are reducing and recycling this mining waste. But it's important, and of course, it's very important to have in mind now more and more the design of sustainable materials. So we need to think not only in the structural properties, cost, and durability of the materials, also in their environmental impact. Of course, during the design of these materials, we must balance the benefits, the environmental benefit, with the properties of the final product and the production cost. and we must make some considerations on the final product. Of course, it never can be harmful to humans and the environment. So that means that there must be a chemical inert. The production must be low cost and environmental friendly. It will never compromise the structural properties and durability of the material. And at the moment, we need to speak about usage limitations and know about the total replacement of raw materials in construction for these waste materials. Well, these are some reference that you can check about the topic. And that's all. Thank you.
Thank you so much, Patricia, for your presentation. There are no questions in the chat. Then we can finish this fourth session. And thank you all for your time, for your presentation. Thank you to the attendees. I hope all of you have found interesting and enriching this day. See you tomorrow for the last day of this workshop. Goodbye.
Bye.
Goodbye.
I think there's a hand.
Sorry?
I think there's a hand, Salmata Diallo. There's
Okay.
a hand.
Yes.
Sure. Because I think
Okay. I allow she to speak. Salmata, when you want.
Hello, I'm just wondering if the former presentation are already on your platform, and how can we access to this presentation? Thank you so much. Do you hear me?
can you repeat, please?
Yes, I was wondering if the former presentation, I mean the presentation of last week, are already in your platform, and how can we access to this presentation? Thank you. Hope that you hear me now.
Yeah, okay, thank you. I think Virginia can tell you, but I think presentations for the last week, I saw them in the virtual congress in the website, I think.
Okay.
But
okay.
I'm not sure. Of course, I will leave my presentation to.
Yes, Patricia, we can provide to the attendees the presentation.
Okay. Okay, I was asking that because before I think that before getting the certification of participating to this webinar, we do have to do a test before. That's why I was asking that question. Thank you.
Yeah, okay. So in my case, I can leave, of course, the presentation, and I think this is recorded, so I'm not sure if they will leave the video.
Appreciate. Thank you.
You're welcome.
Well, we can finish now the session. Thank you again to all. Goodbye.
Thank you. Bye.
Bye.